Good evening, and welcome to The Sleepy Scientist. I'm very glad you've joined me. Before we wander off into the universe, let me know where you're watching from tonight. Maybe you're already tucked into bed, stretched out on the sofa, listening through headphones in a quiet room, or somewhere else entirely. Wherever you happen to be, I hope the day is behind you now, and you can settle in for a while. And if these slow journeys through science have become part of your evenings, leaving a like and subscribing is a lovely way to support the channel. To everyone who has already subscribed and keeps coming back, thank you. It genuinely helps the Sleepy Scientist continue growing. A couple of gentle mentions before we begin. If you'd like to take these journeys with you beyond the videos, there's a Sleepy Scientist ebook available on our website. You'll see a QR code on screen now, and there's a link in the video description too. And we're now uploading episodes to Spotify, so if you'd rather listen with your eyes closed, you can find us there too. That link is in the description as well. Tonight, we're going to follow something rather larger than usual. Not a single planet, star or black hole, but entire galaxies. We'll begin when the universe was young and almost featureless, when tiny differences in density were quietly giving gravity something to work with. From there, we'll watch dark matter gather, the first stars ignite, spiral galaxies take shape. Smaller galaxies disappear into larger ones, and enormous systems gradually run out of the fuel needed to make new stars. And eventually, we'll return a little closer to home, to the Milky Way, Andromeda, and the uncertain future waiting for both of them. So, get comfortable, and let's begin. How are galaxies actually born? How do they grow into structures containing hundreds of billions of stars? And what does it really mean for a galaxy to die? When we look at a galaxy from a distance, it is easy to imagine something permanent, a great island of stars hanging almost motionless against the darkness. But galaxies are not fixed structures. They are changing systems, shaped by gravity, gas, collisions, star formation, and the slow passage of cosmic time. In that sense, galaxies can be thought of as having lives of their own. They are born gradually. They grow, they change shape, they absorb smaller neighbours, they can become more active or less active, and eventually many of them settle into a quieter state, where the production of new stars slows dramatically or stops almost altogether. A galaxy, then, is much more than a collection of stars. At the most basic level, it is a gravitationally bound system. The stars are the most obvious part because they shine, but they are only one component. Between them lies gas, some of it extremely cold and dense, some of it heated to millions of degrees. There is dust, made from tiny solid grains rich in elements forged by earlier generations of stars. There are stellar remnants such as white dwarfs, neutron stars, and black holes. There are magnetic fields stretching across enormous distances, along with high-energy particles known as cosmic rays. And in the centres of many large galaxies, there is a supermassive black hole. But even all of that still describes only the visible, or at least potentially detectable, part of the system. Surrounding the stars and gas is a much larger halo of dark matter. We cannot see dark matter directly because it does not appear to emit, absorb or reflect light in the ordinary way. Its presence is inferred through gravity. Stars orbit galaxies too quickly to be held together by visible matter alone, and the motions of galaxies, the bending of light, and the growth of large-scale structure all point toward the presence of additional unseen mass. So when we picture a galaxy as a bright spiral or a glowing ellipse, we are really looking at only the inner luminous portion of a much larger gravitational structure. Galaxies also come in an extraordinary range of sizes. Some dwarf galaxies contain only a few million stars, and a few of the faintest known examples contain far fewer. At the opposite extreme, giant galaxies can contain hundreds of billions of stars, and the largest may hold numbers reaching into the trillions. Yet size does not tell us everything. A small galaxy is not necessarily young, and a giant galaxy is not necessarily old. Two galaxies of similar mass can have very different colours, shapes, star formation rates, and histories. One may still be rich in cold gas and producing new stars. Another may be dominated by older stars and show very little sign of recent activity. This is one reason it can be misleading to imagine that galaxies are simply born, grow steadily larger, and then die in one neat sequence. Stars have comparatively clear beginnings. A region of gas collapses, a protostar forms, and eventually sustained nuclear fusion begins in its core. A galaxy is messier. There is usually no single moment when an astronomer could point and say that the galaxy suddenly came into existence. Instead, galaxies assemble. Gas falls into growing gravitational structures. Stars form within that gas. Smaller systems merge together. New material continues to arrive from the space around them. Satellite galaxies are captured and stripped apart. Some collisions add stars, others disturb the structure so severely that the entire shape of the galaxy changes. And this process can continue for billions of years. The idea of a galaxy dying is also less dramatic than the word suggests. A dead galaxy does not disappear. Its stars do not all switch off at once, and its gravity does not suddenly weaken. Instead, astronomers usually mean that the galaxy has become passive or quenched. Star formation depends on cold, dense gas. If that gas is used up, heated, removed, or prevented from cooling, the galaxy can no longer produce many new stars. The hot, short-lived blue stars vanish first because they burn through their fuel quickly. Longer-lived redder stars remain, and the galaxy gradually becomes dominated by older stellar populations. It can still shine for an extremely long time. It has simply stopped replacing old stars with large numbers of new ones. Galaxies are also grouped by appearance, although the categories should not be mistaken for simple stages of life. Spiral galaxies have flattened rotating disks with curved arms. Barred spirals contain an elongated structure of stars crossing the centre. Lenticular galaxies have a disk and central bulge, but little obvious spiral structure. Elliptical galaxies are smoother and more rounded or elongated. Irregular galaxies lack the symmetry of the other main types, and dwarf galaxies form a broad family of smaller systems that can themselves be irregular, elliptical, spheroidal, or something in between. Edwin Hubble helped organize these shapes into a famous classification scheme during the early 20th century. It is often shown as the Hubble tuning fork, with elliptical galaxies on one side and spiral and barred spiral galaxies branching away from them. The diagram is extremely useful for describing appearance, but it created a misconception that still occasionally lingers. Hubble's sequence does not mean that one type automatically evolves into the next. A spiral does not simply age until it becomes an elliptical, and an elliptical is not merely an elderly spiral galaxy. Real galactic evolution is far more complicated. To understand how these enormous structures truly form, we have to go much further back than the Milky Way, Andromeda, or any of the mature galaxies visible around us today. We have to return to a time before spiral arms, before galactic disks, before the first stars had begun to shine at all. The young universe was astonishingly smooth, and hidden within that smoothness were tiny differences in density, almost imperceptible variations that gravity would slowly amplify. From those faint irregularities would eventually come every galaxy we see today. In the earliest stages of the universe, there were no galaxies at all. No spiral arms, no elliptical systems, no clusters of galaxies stretching across millions of light years. Matter was distributed with extraordinary smoothness, far more evenly than anything we see in the universe today. And yet it was not perfectly smooth. Hidden within that early uniformity were tiny differences in density. Some regions contained just a little more matter than average. Others contained just a little less. The differences were incredibly small, but gravity is patient, and over immense spans of time those slight irregularities became the starting points for almost everything that followed. Modern cosmology describes this evolution using a framework often called the lambda cold dark matter model. Despite the rather unfriendly name, the basic idea is manageable. The universe is expanding, and its large-scale behavior can be described using several major ingredients. There is ordinary matter, which includes atoms, stars, planets, gas, dust, and everything familiar to us. There is cold dark matter, an unseen form of matter that interacts strongly through gravity and played a central role in the growth of cosmic structure. There is radiation, which was especially important when the universe was young. And there is dark energy, the name given to whatever is responsible for the observed acceleration of cosmic expansion. Within this model, galaxies did not appear suddenly. They developed because those very small early density differences gradually grew. But that raises another question. Where did the density differences come from in the first place? One of the leading ideas involves cosmic inflation. Cosmic inflation proposes that during an extraordinarily early moment in cosmic history, the universe underwent a brief period of extremely rapid expansion. Alan Guth was one of the physicists who helped develop the modern inflationary picture during the late 20th century. The idea was originally introduced to solve several puzzles in cosmology, including why the observable universe appears so remarkably uniform across regions that seem too widely separated to have exchanged information in the ordinary way. Inflation offers another important possibility as well. In quantum physics, even apparently empty space is not perfectly featureless. Very small fluctuations can occur naturally at microscopic scales. During inflation, these tiny variations may have been stretched enormously as space itself expanded. Features that began at subatomic scales could therefore have been expanded across astronomical distances. After inflation ended, these stretched fluctuations would remain as small variations in the density of matter and energy. They were tiny seeds. Gravity did the gardening. Of course, the real physics is rather more complicated than that, but the basic principle is useful. A region containing slightly more matter had slightly stronger gravity. Because its gravity was stronger, it could attract a little more surrounding matter. That increased its density further, strengthening its gravitational pull again. The advantage was extremely small at first, but it accumulated. Meanwhile, regions that began slightly less dense gradually lost matter relative to their surroundings. Over billions of years, many of these lower density regions developed into the enormous cosmic voids that now occupy much of the volume of the universe. The denser regions followed a very different path. They became the foundations of galaxies, galaxy groups, galaxy clusters, and the long filaments of matter that connect them into what astronomers call the cosmic web. There is direct evidence that these early fluctuations existed. It comes from the cosmic microwave background, roughly 380,000 years after the Big Bang. The universe had expanded and cooled enough for electrons to combine with atomic nuclei, producing mostly neutral hydrogen and helium. Before this time, free electrons scattered light so effectively that the universe was filled with an opaque, glowing plasma. Once neutral atoms formed, photons could travel far more freely. That ancient radiation has continued travelling ever since, while the expansion of the universe has stretched its wavelength into the microwave part of the electromagnetic spectrum. Today we observe it as the cosmic microwave background, a faint glow arriving from every direction in the sky. Arno Penzias and Robert Wilson discovered this radiation unexpectedly during the 1960s while working with a sensitive radio antenna. They encountered a persistent background signal that refused to disappear no matter how carefully they checked their equipment. The signal turned out not to be a problem with the antenna. It was the afterglow of the young universe. Later missions mapped that radiation with extraordinary precision. The Cosmic Background Explorer mission provided some of the first convincing measurements of tiny temperature variations across the cosmic microwave background. George Smoot was closely associated with the measurements of those fluctuations, while John Mather led work establishing that the background radiation possessed the near-perfect thermal spectrum predicted for a hot early universe. Later came the Wilkinson Microwave Anisotropy Probe, which mapped the temperature variations in far greater detail. The Planck mission improved the measurements again, producing extremely precise maps of the early universe and allowing cosmologists to estimate important properties such as its age, composition, and geometry. The most striking feature in these maps is how small the variations actually are. The temperature differences are only around 1 part in 100,000. If the cosmic microwave background had exactly the same temperature everywhere, there would be no obvious seeds from which later structure could develop. Instead, it contains an intricate pattern of slightly hotter and slightly colder regions. Those small differences reflect variations in the density and motion of matter in the early universe. They are, in a very real sense, a baby picture of the structure that would eventually become galaxies. From something as smooth as the early universe, this may seem almost impossible. But gravitational instability means that perfectly dramatic beginnings are not required. A slightly denser region does not need to collapse immediately. It simply needs to have a small gravitational advantage over its surroundings. Given enough time, that difference grows. Matter falls toward denser regions. Those regions become denser still. Their gravitational attraction becomes stronger, and the process continues. Across hundreds of millions of years, tiny irregularities can become enormous structures. There is one major difficulty, however. Ordinary matter could not have done all of this efficiently enough on its own. In the early universe, ordinary matter was tightly coupled to radiation for a long period, and its ability to collapse into structure was limited. If galaxies had depended entirely on normal atomic matter, beginning its growth only after the cosmic microwave background was released, the structures seen in the modern universe would have been extremely difficult to assemble as quickly as observations show they did. Something else had already begun building gravitational foundations. It did not shine. It did not form atoms. And yet its gravity would guide much of the matter that later became stars and galaxies. That invisible foundation was dark matter. Dark matter is one of the strangest ingredients in the story of galaxies, partly because we cannot see it directly at all. It does not appear to emit light. It does not seem to absorb light in the ordinary way, and it does not reflect light back toward us. If dark matter were sitting alone in empty space, there would be no obvious glow announcing that it was there. Its presence is revealed through gravity. We can watch how stars move inside galaxies, how galaxies move inside clusters, how light bends while passing massive structures, and how the large-scale universe developed from its early state. Again and again, the amount of visible matter is not enough to explain what gravity appears to be doing. This invisible component is not simply ordinary material hidden in the dark. It cannot be explained by vast clouds of faint gas, enormous numbers of dim stars, or dust that happens to be difficult to see. Observations of the cosmic microwave background, the abundance of light elements produced in the early universe, gravitational lensing, galaxy clusters, and galactic rotation all point toward a form of matter that is fundamentally different from ordinary atomic matter. Physicists often describe it as non-baryonic matter, meaning that it is not made primarily from protons and neutrons in the familiar way that stars, planets, gas, and people are. The evidence emerged gradually. During the 1930s, the astronomer Fritz Zwicky studied galaxies moving within the Coma cluster. A galaxy cluster is held together by gravity, so the speeds of its galaxies provide information about how much mass the cluster contains. Zwicky found that the galaxies appeared to be moving far too quickly for the visible stars alone to keep the cluster gravitationally bound. There seemed to be a large amount of missing mass. At the time, this was intriguing, but not yet enough to establish the modern picture of dark matter. Several decades later, another line of evidence became extremely influential. Vera Rubin, working with the astronomer Kent Ford, measured how stars and glowing gas moved around spiral galaxies. If most of a galaxy's mass were concentrated where most of its visible light was concentrated, then stars farther from the centre should generally orbit more slowly, in much the same way that distant planets move more slowly around the Sun. That was not what the observations showed. Far from galactic centres, orbital speeds often remained surprisingly high. These measurements became known as flat rotation curves. The simplest explanation was that the visible disk sat inside a much larger distribution of unseen mass. The farther outward astronomers looked, the more gravitational influence remained, even where there was relatively little starlight. This was powerful evidence for extended dark matter halos surrounding galaxies. Dark matter was also crucial long before mature spiral galaxies existed. The leading cosmological model describes most dark matter as cold dark matter. Cold does not mean that it is literally at a low temperature in the everyday sense. It means that the particles were moving slowly enough relative to the expansion of the early universe for gravity to gather them efficiently into increasingly dense structures. Small concentrations formed first. These merged with other concentrations and grew into larger structures over time. This process is known as hierarchical structure formation. Instead of the largest galaxies and clusters forming immediately, smaller dark matter halos generally appeared earlier and gradually combined into larger halos. Across enormous scales, gravity pulled these structures into the cosmic web. Matter did not simply gather into isolated round clumps scattered randomly through space. It formed filaments stretching across millions of light years, broad sheets of matter, dense intersections called nodes, and enormous underdense regions known as cosmic voids. Galaxies eventually became concentrated along these filaments, and especially around the dense nodes where filaments met. Dark matter therefore provided more than extra gravity inside individual galaxies. It helped determine the architecture of the entire large-scale universe. Within this growing web, each dark matter halo acted as a gravitational well. Ordinary hydrogen and helium could fall into these wells. As more matter accumulated, the gravitational potential deepened, making it easier for additional material to remain bound. This is why dark matter halos are often described as the foundations of galaxies. The visible galaxy formed inside the halo, rather than the halo somehow appearing later, around an already finished galaxy. But a halo should not be imagined as a rigid, invisible shell. It is a dynamic structure. A dark matter halo can grow by attracting material from its surroundings. It can merge with other halos. It can contain smaller subhalos orbiting within it, many of which may host dwarf galaxies or may contain almost no visible matter at all. Its shape can change, its mass can increase, and its motion responds continuously to the gravitational environment around it. During the late 20th century, Simon White and Martin Rees helped develop an influential picture of galaxy formation built around these ideas. In this framework, dark matter halos collapse and grow first, while ordinary gas falls into them, cools, and eventually forms the visible parts of galaxies. This basic picture remains central to modern galaxy formation theory, although the details have become vastly more sophisticated. Computer simulations now attempt to follow both dark matter and ordinary matter together. Dark matter is comparatively simple to model because it behaves mainly through gravity and rarely collides with itself in the conventional picture. Gas is much more troublesome. Gas has pressure. It can be heated and cooled. It can become turbulent. It can collapse into dense clouds, form stars, absorb radiation, emit radiation, become enriched with heavy elements, and be thrown outward again by stellar explosions or energetic black holes. A realistic galaxy simulation, therefore, has to follow an enormous range of physical processes occurring across very different scales. Even with all this evidence for dark matter, its actual identity remains unknown. Several possible particles have been proposed. Weakly interacting massive particles were long considered especially promising candidates. Axions are another major possibility. Other models suggest still different particles or hidden sectors of physics. None has yet been confirmed as the dark matter particle, so dark matter occupies an unusual position in modern science. Its gravitational effects are seen throughout the universe, yet whatever produces those effects has not been directly identified. Still, the role it appears to have played in galaxy formation is profound. Before the first galaxies could shine, dark matter had already begun gathering into halos. Those halos deepened into gravitational wells, and ordinary hydrogen and helium started falling inward. Unlike dark matter, however, gas could collide, heat up, radiate energy away, and gradually become denser. Only when enough of that gas cooled and collapsed would the darkness finally be interrupted. The first stars were about to begin shining. After the cosmic microwave background was released, the universe entered a long period with no stars at all. There was matter everywhere, but very little visible light. Hydrogen and helium filled space. Dark matter had already begun gathering into halos and larger structures, but the familiar sources of light that now fill the universe had not yet formed. Astronomers call this period the Cosmic Dark Ages. It began after the universe became transparent, roughly 380,000 years after the Big Bang, and continued until the first stars started to appear. During this time, ordinary gas was slowly responding to gravity. Hydrogen and helium fell into the growing dark matter halos that had already begun forming throughout the young universe. As more gas accumulated in these gravitational wells, it became compressed. Compression increased the density, and if the gas could somehow lose enough energy, gravity could pull it inward even further. Cooling was therefore essential. Modern star-forming clouds contain elements such as carbon and oxygen, as well as dust grains that help gas radiate energy efficiently. None of those ingredients were available at the beginning. The early universe contained almost nothing heavier than hydrogen, helium, and tiny traces of a few other light elements. One important route for cooling involved molecular hydrogen. Molecular hydrogen forms when two hydrogen atoms become bound together. Even in the chemically simple early universe, small amounts could form inside sufficiently dense regions. These molecules were able to radiate away some of the thermal energy in the gas. As the gas cooled, pressure became less effective at resisting gravity. Dense regions contracted. Eventually, portions of these clouds became compact enough for the first stars to form. Astronomers usually refer to this hypothetical first generation as population 3 stars. The name can sound slightly backwards. Population 1 stars, including the Sun, tend to contain comparatively large amounts of elements heavier than helium. Population 2 stars are generally older and contain fewer of those elements. Population 3 refers to an even earlier generation, formed before stars had produced significant quantities of heavier elements at all. These first stars would therefore have consisted almost entirely of hydrogen and helium. No individual population 3 star has yet been securely identified. That does not mean the idea is simply speculative decoration. Their existence follows naturally from cosmic chemical evolution. Heavy elements such as carbon, oxygen, silicon, and iron had to be created somewhere. Since the early universe began with almost none of them, there must have been an earlier generation of stars that formed from much more chemically primitive material. Exactly what those stars were like remains an active area of research. Many simulations suggest that at least some population 3 stars could have been substantially more massive than typical stars forming in the Milky Way today. Without heavy elements and dust, primordial gas cooled differently. That could encourage larger collapsing fragments, and therefore larger stellar masses. But it would be misleading to say that every first-generation star must have been an enormous monster. The exact distribution of their masses remains uncertain. What is clearer is that once the first stars appeared, they began changing the universe around them. Massive stars emit intense ultraviolet radiation. Their radiation heated nearby gas and altered its chemistry. Their stellar winds pushed material outward. And because massive stars live relatively short lives, some eventually exploded as supernovae. Those explosions were especially important. Inside stars, nuclear reactions produce heavier elements. Additional elements are created during some stellar explosions. When the first supernovae scattered this material into surrounding space, the universe became chemically richer. Carbon appeared in greater quantities. So did oxygen, silicon, iron, and many other elements that would later become essential ingredients of planets, rocks, atmospheres, and eventually life. The earliest galaxies were therefore not calm, beautifully organized spirals. They were small, turbulent, irregular systems. Gas flowed inward. Stars formed in uneven bursts. Supernovae pushed material back out. Dark matter halos merged. Small protogalaxies collided and combined with one another. Their shapes changed repeatedly. The first galaxies were less like finished cosmic islands and more like construction sites that happened to be glowing. Their radiation also helped drive one of the largest transformations in cosmic history. This process is known as cosmic reionization. After the cosmic microwave background was released, most hydrogen in intergalactic space became electrically neutral. Later, energetic ultraviolet photons began knocking electrons away from hydrogen atoms again. Over hundreds of millions of years, large regions of intergalactic hydrogen became ionized. Astronomers think young galaxies containing hot massive stars probably supplied much of the ultraviolet radiation required for this transformation. But the full story is still being worked out. Extremely faint galaxies may have contributed heavily simply because there were so many of them. Massive stars were almost certainly important. Accreting black holes may also have played a role. and one crucial uncertainty concerns how much ionizing radiation could actually escape from the gas and dust inside early galaxies and reach intergalactic space. This era is now being observed in far greater detail than was possible only a short time ago. The James Webb Space Telescope was designed partly to study this distant universe. It is an international mission involving the National Aeronautics and Space Administration, the European Space Agency, and the Canadian Space Agency, with scientific operations supported by the Space Telescope Science Institute. Because the universe has been expanding, light from extremely distant galaxies is stretched toward longer wavelengths. This effect is called redshift. The farther back astronomers look, the greater the redshift tends to be. And because light travels at a finite speed, looking across enormous distances is also looking backward in time. A galaxy seen more than 13 billion light-years away is not being observed as it exists now. Its light began travelling toward us when the universe itself was extremely young. This is called look-back time, and it allows telescopes to study stages of galaxy formation that disappeared billions of years ago. The James Webb Space Telescope has revealed surprisingly bright and apparently developed galaxies from within the first few 100 million years of cosmic history. Some appear to have assembled stars more quickly than earlier models had expected. These observations have created useful tension between theory and evidence. They have not shown that the standard cosmological picture is simply wrong. Instead, they are forcing astronomers to refine estimates of how efficiently early galaxies formed stars, accumulated gas, produced dust, and grew inside their dark matter halos. By this point, the universe had changed profoundly. There were now stars where once there had been none. There were supernovae producing heavier elements. There were young galaxies emitting radiation into surrounding space. Gas was being heated, cooled, enriched, expelled, and drawn back inward. Gravity had turned tiny early density fluctuations into genuine luminous structures. But these first galaxies were still small compared with many of the enormous systems seen around us today. To become larger, they needed a continuing supply of material. Gas would have to keep arriving, halos would have to keep growing, and over immense periods of time, these chaotic early systems would begin developing something more organized. For a young galaxy to grow, it needs more than stars already shining inside it. It needs a continuing supply of ordinary matter. Much of that material comes from the vast cosmic web, where gas traces the same enormous filaments of matter that connect groups and clusters of galaxies across the universe. A young dark matter halo does not sit in isolation. It is embedded within this network, and gravity continually draws fresh material inward. Some of that gas can arrive relatively cool. Other gas is heated dramatically as it falls into the halo. When rapidly moving material encounters denser gas already surrounding a galaxy, shocks can form. These shock waves convert some of the gas's motion into heat, raising temperatures to hundreds of thousands or even millions of degrees. So around a growing galaxy, there can be a vast region of diffuse material existing in many different states. Astronomers call much of this the circumgalactic medium. The circumgalactic medium surrounds the visible part of a galaxy and extends far beyond its stars. It is not empty space. It can contain hot plasma, cooler gas, chemically enriched material expelled by earlier generations of stars, and fresh matter arriving from the intergalactic environment. It acts almost like a reservoir between the galaxy and the larger universe. Gas can flow inward from it. Gas can also be thrown outward into it by supernova explosions, stellar winds, or activity around a central black hole. Some of that expelled material may later return. In this way, a galaxy is constantly exchanging matter with its surroundings. For gas to settle deeper into the halo and help build the visible galaxy. However, it usually needs to lose energy. This happens partly through radiative cooling. Hot gas contains rapidly moving particles. When those particles interact, the gas can emit electromagnetic radiation and lose energy. As it cools, pressure becomes less effective at supporting the gas against gravity. The material can then sink farther inward. But it does not simply fall in a perfectly straight line toward the center. Almost all infalling matter possesses some angular momentum. Angular momentum is the tendency of moving material to continue rotating around a center rather than dropping directly into it. Even a very small amount of sideways motion can become important as gas collapses inward. A familiar comparison is a spinning skater drawing in their arms. As the skater becomes more compact, the rotation speeds up. Something broadly similar happens with collapsing gas. As material moves closer to the center while roughly conserving angular momentum, its rotational motion becomes increasingly important. Instead of disappearing into one dense central point, much of the gas begins orbiting. Collisions between gas clouds also matter. Because ordinary gas can collide, compress, radiate energy, and exchange angular momentum. Some material loses orbital energy, while angular momentum is redistributed through the system. Over time, the gas can settle into a rotating flattened structure. This is one of the main routes by which a galactic disk forms. Dark matter behaves differently. In the standard picture, dark matter particles do not interact electromagnetically in the ordinary way. They cannot radiate heat efficiently, collide into dense clouds, and cool into a thin layer of the kind formed by ordinary gas. Dark matter therefore remains distributed through a much broader halo, rather than settling into the thin luminous disk. The early galactic disks that formed within these halos were probably not always the calm. Delicate structures seen in many nearby spiral galaxies today. They could be thick. They could be turbulent. They could contain enormous clumps of dense gas, some of them producing stars at very high rates. The motions of gas were continually disturbed by material arriving from different directions. A young galaxy might also experience repeated mergers with smaller systems, adding stars, gas, and angular momentum while disrupting whatever orderly structure had already developed. Even mature disk galaxies contain several distinct components. A thin stellar disk contains much of the younger stellar population and much of the cold gas where active star formation continues. A thick disk extends farther above and below the galactic plane and generally contains older stars with less orderly orbits. Near the center, many galaxies possess a bulge, a dense concentration of stars whose origins may involve early collapse, mergers, or slower internal processes. Beyond the bright disk lies a much more diffuse stellar halo containing old stars, globular clusters, and the remnants of smaller galaxies absorbed over cosmic time. These parts do not necessarily appear in one fixed order. A galaxy's structure can be assembled, disturbed, and rebuilt repeatedly. Minor mergers can thicken a disk by giving stars more random motions. A small satellite passing through or near a galaxy can distort its structure gravitationally. Incoming gas may arrive with angular momentum, pointing in a slightly different direction from material already present. Gravitational torques can move angular momentum from one region to another. Internal instabilities can produce bars, rings, or concentrations of gas near the center. Sometimes an existing disk is damaged. Sometimes new gas settles afterward and helps create another one. So disk formation is not really a single event. It is an extended process that can continue for billions of years. A galaxy remains connected to its environment for much of its life, constantly gaining, losing, cooling, heating and rearranging material. The visible disk at any particular moment is therefore the temporary result of everything that has happened before. And once enough gas has cooled into the disk, gravity begins concentrating it even further. Dense clouds form. Parts of those clouds become colder and more compact. Eventually, some collapse until new stars ignite inside them. Those stars will return energy and matter to the gas around them. Some will end in supernova explosions. The next generation of gas will be mixed, heated, enriched, and compressed again. Galactic growth becomes a cycle. Gas falls inward. Stars form. Stars return material. Some gas escapes. Some comes back. And over immense periods of time, the galaxy slowly builds itself from that continuing exchange between gravity, radiation, motion, and matter. Deep inside a growing galaxy, star formation begins in some of its coldest and densest regions. These regions are found within molecular clouds, enormous collections of gas where temperatures can fall low enough for molecules to survive, and where gravity can begin gathering matter into smaller and denser structures. A molecular cloud is not perfectly still. Gas moves through it. Turbulence creates knots and filaments. Magnetic fields provide additional support. Internal pressure resists collapse. But in some places, gravity eventually becomes stronger than those competing effects. Dense cores begin to contract. As they collapse, their density rises further, and some eventually become protostars. This means that simply having a large quantity of gas does not guarantee that a galaxy will form stars rapidly. Much of a galaxy's gas may be too hot, too diffuse, or too turbulent to collapse. Only a fraction is cold and dense enough to participate directly in star formation. Astronomers have found a broad observational relationship between the amount of gas packed into a region and the rate at which that region forms stars. This is known as the Kennicutt-Schmidt relation, named for Martin Schmidt and Robert Kennicutt. In general, regions containing higher surface densities of gas tend to form stars more rapidly. It is not a perfect rule for every cloud or every galaxy, but it captures an important principle. Dense gas makes star formation easier. Once stars begin forming, however, they immediately start changing the conditions that allowed them to exist. The most massive young stars are particularly influential. They shine intensely in ultraviolet light, heating and ionizing nearby gas. They produce powerful stellar winds that push material away from their surfaces at tremendous speeds. And because massive stars burn through their nuclear fuel quickly, some end their lives after only a few million years in enormous supernova explosions. All of these processes inject energy and momentum into the surrounding interstellar medium. Together, their effects are known as stellar feedback. Feedback can slow star formation by disrupting the very clouds from which stars are forming. Radiation and stellar winds can carve cavities through dense gas. Supernova explosions can tear molecular clouds apart. A region that seemed ready to produce many more stars may suddenly find much of its material scattered and heated. Yet stellar feedback is not purely destructive. A shock wave travelling through nearby gas can compress it. If the compressed region becomes dense enough, gravity may take advantage of the disturbance and trigger new collapse. So one generation of stars can both suppress and encourage the formation of another. Galaxies therefore regulate themselves through a complicated balance between collapse and disruption. Supernova explosions can affect material far beyond the immediate star-forming region. When many explosions occur within a galactic disk, they can heat gas so strongly that some of it rises thousands of light-years above the plane. This process can create a galactic fountain. Hot material flows upward into the galactic halo, where it expands and cools. Some of it may later lose enough energy to fall back toward the disk. The gas has not necessarily escaped the galaxy, it has simply taken a rather large detour. In smaller galaxies, the outcome can be more dramatic. Dwarf galaxies have relatively shallow gravitational wells. A sufficiently energetic burst of stellar feedback can therefore push gas outward strongly enough that some of it escapes altogether. This makes supernovae and stellar winds especially important in regulating the growth of low-mass galaxies. At the same time, dying stars are doing something equally important. They are changing the chemistry of the gas. The early universe was made almost entirely from hydrogen and helium, with only tiny amounts of a few other light elements. Inside stars, nuclear fusion creates heavier nuclei. Massive stars manufacture elements such as carbon, oxygen, neon, magnesium and silicon during different stages of their lives. Supernova explosions produce and disperse additional elements, while other stellar processes contribute still more. Over repeated generations, the interstellar medium becomes chemically enriched. Astronomers often refer to every element heavier than helium as a metal. This can sound slightly strange. Oxygen, for example, is certainly not a metal in the everyday chemical sense, but in astronomy it counts. As galaxies evolve, their stars and gas generally become richer in these heavier elements. That enrichment changes future star formation. Dust grains can condense from material produced by stars. These tiny particles help gas cool. They shield molecules from destructive radiation. They provide surfaces on which important chemical reactions can occur, and they become part of later planetary systems. This creates a direct connection between galactic evolution and our own existence. Rocky planets require elements such as silicon, magnesium, oxygen, and iron. Carbon-based chemistry depends on elements that simply did not exist in meaningful quantities when the universe was young. The atoms that later became planets, oceans, rocks, and living organisms had to be manufactured by earlier stars and returned to space. Galaxies are therefore not only factories for stars, they are recycling systems. Gas collapses, stars form, stars alter the gas around them. Some die and return enriched material to space. That material cools, mixes and becomes available to future generations. And in a rotating galactic disk, these young stars are rarely distributed in a perfectly uniform pattern. Instead, many of the brightest gather along enormous curved structures, stretching across thousands of light years. From a distance, those concentrations of young stars, gas and dust appear as the graceful spiral arms of a galaxy. Spiral galaxies are among the most recognizable structures in the universe. Their bright disks curve outward in sweeping arms filled with stars, gas and dust, often wrapping around a dense central bulge. From a distance, they can look almost deliberately arranged, as though enormous streams of stars have been painted into place. But the spiral arms are not rigid structures. The same stars do not remain inside the same arm forever. A galaxy is rotating continuously, and individual stars orbit around its centre on their own paths. Gas clouds move as well. The spiral pattern can persist even though much of the material making it visible is constantly entering and leaving different parts of that pattern. This distinction becomes important because of something known as the winding problem. Material closer to the centre of a spiral galaxy usually completes an orbit more quickly than material farther away. If spiral arms were simply permanent rows of stars rotating with the disk, the inner portions would race ahead of the outer portions. The arms would wind tighter and tighter with every galactic rotation. After enough time, the elegant open spirals seen across the universe should become hopelessly twisted. Yet many galaxies have maintained prominent spiral patterns for billions of years. Clearly, something more interesting is happening. One influential explanation is density wave theory. During the 20th century, Chia-Chow Lin and Frank Hsu developed a mathematical description in which spiral arms could behave as regions of enhanced density moving through a galactic disk. The stars themselves do not necessarily travel around the galaxy permanently locked inside these arms. Instead, stars and gas can move into a denser region and eventually move out again, while the broader spiral pattern remains visible. A useful comparison is a traffic jam on a motorway. The congestion can remain in roughly the same area for some time, even though the individual cars entering it are constantly changing. A car approaches, slows down, passes through the crowded region, and eventually leaves. The traffic jam remains even though it is no longer made from exactly the same cars. Spiral arms can behave in a loosely similar way. Stars may pass through them while the denser pattern survives for much longer. Gas responds even more strongly. As interstellar gas enters a denser spiral region, it can become compressed. Clouds may collide or accumulate more material, increasing the chance that portions of them will become cold and dense enough to collapse gravitationally. New stars then begin forming. Massive young stars are particularly noticeable because they are extraordinarily luminous and hot. They tend to shine strongly at blue and ultraviolet wavelengths. So many spiral arms appear distinctly blue in astronomical images. This does not mean that most stars in the galaxy are permanently trapped inside the arms. Older stars can be found throughout the disk. The arms simply become especially visible because they contain concentrations of gas, dust, and bright young stars. Density wave theory provides an elegant explanation for some spiral structure, but it is not a universal answer. Not every spiral galaxy has the same kind of arms. Some have two broad, prominent arms extending around much of the disk. Others display many shorter, fragmented sections. These are sometimes described as flocculent spiral galaxies because their patterns look patchier and less orderly. Local gravitational instabilities within a disk can help produce these shorter features. A small overdensity can attract more material. That extra material strengthens the local gravitational disturbance. Temporary spiral segments can emerge, fade, and later reform somewhere else. Computer simulations suggest that spiral structure can therefore be transient and recurrent, rather than one permanent wave surviving unchanged for the entire life of a galaxy. Nearby galaxies can also help create spiral patterns. A close gravitational encounter can pull strongly on a galactic disk. Different regions experience slightly different gravitational forces, producing tidal distortions that can develop into striking spiral arms. The Whirlpool Galaxy provides a famous example. Its smaller companion galaxy has interacted gravitationally with the larger spiral, and that interaction is thought to have helped strengthen the Whirlpool Galaxy's prominent arm structure. So there may be several ways to produce what we casually call a spiral galaxy. Long-lived density patterns can contribute, temporary gravitational instabilities can contribute, neighbouring galaxies can contribute, and in many real systems, several of these processes may be operating at the same time. Some spiral galaxies possess another enormous structure across their centres. This is a galactic bar. A bar is an elongated concentration of stars extending through the central region of a disk. Bars are themselves dynamic gravitational structures. They can exchange angular momentum with other parts of a galaxy and influence the motion of both stars and gas. Gas responding to the gravitational pull of a bar can gradually be channeled inward toward the central regions. This can help create dense rings of star formation and may influence the supply of material reaching the immediate surroundings of a central supermassive black hole. Our own Milky Way is a barred spiral galaxy. Its stellar disk is roughly 100,000 light-years across, although the much more diffuse outskirts of the galaxy extend farther. From our position inside that disk, however, mapping its exact spiral pattern is surprisingly difficult. We cannot simply step outside and photograph the Milky Way from above. Instead, astronomers reconstruct its structure by measuring stars, gas clouds, radio emission, distances and motions throughout the disk. Several major spiral arms and smaller features have been identified, but the precise arrangement is still refined as new observations become available. From elsewhere in the universe, a galaxy like ours would probably appear far more straightforward. A broad, luminous disk, a central bar, curving arms marked by clouds of gas and young stars. But even that graceful shape is temporary on cosmic timescales. Galaxies can be disturbed. Their gas can disappear. Their disks can thicken. Mergers can rearrange billions of stellar orbits. And some galaxies contain little obvious spiral structure at all. In those systems, orderly rotation becomes less visually dominant, and the shapes begin changing from flattened spirals into something smoother, rounder, and very different. Galaxies rarely fit into perfectly tidy categories. Astronomers use labels such as spiral, elliptical, lenticular, and irregular because those descriptions are useful. They help organize the enormous variety of shapes seen across the universe. But real galaxies occupy a broad spectrum, and many sit somewhere between the familiar textbook examples. Their structures can overlap. A spiral galaxy may have an enormous central bulge. Another may have only a modest one. Some possess strong bars, while others show none at all. Some disks are rich in gas and bright young stars, while others are smooth, faint, and almost completely quiet. The central bulge is one of the most important structures in many disk galaxies. A classical bulge is a dense, roughly rounded concentration of stars near the centre. Its stars tend to move on more varied and disordered orbits than stars in the thin disk, where motion is dominated by rotation around the galactic centre. Classical bulges often contain older stellar populations and can resemble small elliptical galaxies embedded inside larger disks. But not every bulge formed in the same way. Some galaxies contain what astronomers call pseudobulges. These tend to be flatter and more closely connected to the surrounding disk. They may rotate more strongly than classical bulges, contain appreciable amounts of gas, and sometimes continue forming new stars. Rather than being created primarily through an ancient major merger, a pseudobulge can develop gradually as material inside a disk is rearranged over billions of years. One of the most important structures involved in that slow rearrangement is a galactic bar. A bar forms when a rotating stellar disk develops a large-scale gravitational instability. Instead of stars remaining distributed in a roughly circular pattern around the centre, many of their orbits become aligned in a way that creates an elongated structure crossing the inner galaxy. Bars are common, and once they form, they can influence the evolution of the entire disk. A bar interacts gravitationally with stars, gas, and the surrounding dark matter halo. Through these interactions, angular momentum can be transferred from one region of the galaxy to another. Gas is particularly responsive because it can collide, lose energy, and change orbit. The gravitational influence of a bar can therefore guide gas inward. Some of that gas may collect in rings around the central region, where it can become dense enough to form new stars. Some may travel closer to the central supermassive black hole. potentially supplying material that can later power activity around it. These processes show how a galaxy can change significantly even without colliding with another large galaxy. Slow internal evolution can be surprisingly effective. Astronomers call this secular evolution. The word secular here simply means gradual change occurring over long periods rather than a sudden transformation caused by a violent external event. Bars can grow, gas can migrate inward, stellar orbits can be rearranged, central regions can become denser, spiral patterns can weaken. Over billions of years, these changes can alter a galaxy's appearance, even if no major merger takes place. Some galaxies sit particularly clearly between the familiar spiral and elliptical forms. These are lenticular galaxies. A lenticular galaxy contains a flattened disk and usually a prominent central bulge, rather like a spiral. But it has little obvious spiral structure. It also tends to contain less cold gas and less active star formation than a typical spiral galaxy. From a distance, a lenticular galaxy can look almost like a smooth glowing lens. There is no single agreed pathway that produces every lenticular galaxy. Some may begin as spirals and gradually lose the cold gas needed to maintain strong star formation. Others may have their gas stripped away by the environment around them. Some may experience minor mergers that thicken and disturb the disk without completely destroying it. Repeated gravitational encounters can heat stellar orbits. And if star formation declines, the bright young stars that once highlighted spiral arms disappear, allowing those patterns to fade from view. So a galaxy can move toward a smoother appearance without undergoing one spectacular collision. This makes galactic history difficult to read from shape alone. During the 20th century, Grade de Vaucouleurs expanded galaxy classification beyond the original Hubble sequence, creating a more detailed system that recognized the wide range of intermediate forms, bars, rings, and spiral structures seen in real galaxies. That added complexity reflected an important truth. Morphology describes what a galaxy looks like now. It does not necessarily tell us exactly how it arrived there. Two galaxies with almost identical shapes may have experienced very different histories. One may have grown quietly by drawing gas from its surroundings. Another may have lost its gas inside a crowded galaxy cluster. A third may have absorbed several smaller companions. A fourth may have been transformed mainly by its own internal bar and gravitational instabilities. Accretion, stellar feedback, environment, mergers, and internal evolution can all contribute to the final appearance. Galaxies are therefore less like objects assigned permanently to fixed categories, and more like systems continually being reshaped by their histories. Some remain dominated by graceful rotating disks. Some lose their spiral structure but keep the disk itself. Others become far more rounded, with stars moving in many different directions and little sign of the ordered rotation that once may have existed. And this raises a larger question. If slow internal changes can transform a spiral only so far, what creates the enormous smooth elliptical galaxies seen throughout the universe, including some of the largest galaxies ever observed? Elliptical galaxies look very different from the graceful disks and spiral arms that often come to mind when we picture a galaxy. Instead of a thin rotating structure, an elliptical galaxy is usually smooth, rounded, or stretched into an elongated shape. Its stars move in many different directions. There may still be some overall rotation, but the motion is not dominated by one thin organized disk in the way it is inside a typical spiral galaxy. Instead, the stars follow a wide range of orbits around the common gravitational center. Elliptical galaxies also come in an enormous variety of sizes. Some are relatively small and compact. Others are truly immense. The largest can occupy the centers of massive galaxy groups and clusters, containing vast populations of stars spread across hundreds of thousands of light years. Many of these giant systems possess extended outer envelopes that gradually fade into the surrounding cluster environment. Despite their size, large elliptical galaxies often look surprisingly calm. Their light tends to be distributed smoothly. They usually contain less cold molecular gas than actively star-forming spiral galaxies. Their average stellar populations are generally older. And because they have less cold gas available for collapse, many produce comparatively few new stars today. This gives them a redder appearance overall, because the bright blue stars associated with recent star formation have largely disappeared. It would be tempting to imagine ellipticals as galaxies that simply formed early and then remained unchanged. But that picture is much too simple. Many elliptical galaxies have experienced long and complicated histories. One important route involves major mergers. A major merger occurs when two galaxies of broadly comparable mass interact and eventually combine. If both contain stellar disks, the encounter can seriously disturb the ordered structure of those disks. As the galaxies pass through one another, their combined gravitational field changes rapidly. Stars that once followed relatively organized orbits can be thrown onto very different paths. Over time, the system can settle into a much rounder remnant in which stellar motion is supported more by random velocities than by one coherent rotating disk. One process involved in this transformation is known as violent relaxation. The idea is associated particularly with Donald Lyndon Bell. Despite the dramatic name, violent relaxation does not mean that stars are colliding violently with one another. Instead, it refers to the rapid redistribution of stellar energies while the overall gravitational potential of the system is changing during a merger or collapse. A star moving through that changing gravitational field can gain or lose orbital energy. Across billions of stars, this helps erase much of the ordered structure that existed before. The result can be a smoother, more pressure-supported galaxy. This distinction matters because individual stars almost never collide during a galaxy merger. A galaxy may contain hundreds of billions of stars, but those stars are separated by enormous distances. Even when two galaxies overlap almost completely, the space between their stars is so large that direct stellar impacts remain extremely rare. The galaxies pass through each other gravitationally far more than their stars physically crash together. Gas behaves very differently. Gas clouds can collide, they can compress, they can radiate energy away, they can lose angular momentum and fall toward the central regions. In a gas-rich merger, this can trigger intense episodes of star formation. Large quantities of cold gas may be compressed into dense clouds, producing what astronomers call a starburst. At the same time, some gas may be funneled inward toward the central, supermassive black holes. So a merger can briefly make a galaxy extremely active before much of its usable cold gas is consumed, heated, or expelled. Even here there is no single recipe. Not every major merger creates a giant elliptical galaxy. And not every elliptical formed through one dramatic collision between two spirals. Some may have developed through repeated minor mergers, slowly adding smaller galaxies over billions of years. Others may have formed much of their central structure early through rapid collapse involving gas that could efficiently lose energy. Environment also matters. Galaxies living near the centers of massive groups and clusters experience very different histories from isolated galaxies drifting through quieter regions. For the largest ellipticals, growth can continue long after most star formation has faded. These galaxies may undergo what astronomers call dry mergers. A dry merger involves galaxies containing relatively little cold gas. Because there is not much gas available to compress into new stars, the collision adds mainly existing stars rather than producing a spectacular new burst of star formation. Repeated dry mergers can gradually build enormous central galaxies while leaving their stellar populations old and relatively quiet. Astronomers can study the internal motions of these systems using something called stellar velocity dispersion. Instead of asking only how quickly the whole galaxy rotates, they measure the range of speeds at which stars move toward and away from us. A high-velocity dispersion means that the stars possess a broad spread of orbital velocities. Because those motions are controlled by gravity, they provide information about how much mass is required to hold the system together. This helps astronomers estimate the mass of elliptical galaxies and compare their internal structure with their visible light. So the smooth appearance of an elliptical galaxy hides a surprisingly complicated history. Its rounded shape may preserve the effects of mergers, gravitational rearrangement, gas loss, starbursts, and billions of years of accumulated growth. Some are among the largest stellar systems in the universe, but they are not the most numerous kind of galaxy. Across the cosmos, far smaller systems are everywhere. Dwarf galaxies may be faint, easily overlooked, and sometimes only loosely organized, yet they are fundamental to understanding how larger galaxies were assembled in the first place. Dwarf galaxies are easy to underestimate. They are smaller and fainter than the great spirals and ellipticals that dominate many astronomical images, but they are among the most important systems in the story of galaxy formation. Depending on the type, a dwarf galaxy may contain only thousands or millions of stars, while larger examples can contain several billion. That is still modest compared with the hundreds of billions of stars in a galaxy like the Milky Way. But small does not mean unimportant. In the hierarchical picture of galaxy formation, smaller structures tend to form first and then combine over time. Dark matter halos merge, gas gathers inside them, small stellar systems appear, and many of those early systems are later absorbed into larger ones. A galaxy such as the Milky Way is therefore not simply one enormous object that formed all at once. Part of its history is written in the remains of smaller galaxies that were gradually added to it. Some dwarf galaxies are still rich in gas. These are often classified as dwarf irregular galaxies. They tend to lack the elegant symmetry of a spiral galaxy, with stars and gas distributed in a more uneven pattern. Bright regions of recent star formation may appear scattered across them. The Large Magellanic Cloud is a good nearby example. It contains substantial amounts of gas and continues to form new stars, including in prominent regions such as the Tarantula Nebula. Other dwarfs are very different. Dwarf spheroidal galaxies are usually faint, diffuse, and poor in cold gas. They are often dominated by old stars and are commonly found orbiting much larger galaxies. Several dwarf spheroidals surround the Milky Way. Although their visible stellar populations can be extremely modest, measurements of how their stars move suggest that many contain much more mass than the stars alone can explain. This makes dwarf galaxies especially interesting for studying dark matter. In some of the faintest known systems, the inferred dark matter mass can greatly exceed the mass contained in visible stars. Astronomers can estimate this by measuring the velocities of stars moving inside the galaxy. If the stars are moving too quickly to be held together by their visible mass alone, additional gravitational influence is required. dark matter is the leading explanation. Dwarfs therefore provide laboratories for studying how dark matter behaves on scales much smaller than those of giant galaxies or galaxy clusters. Their small size also makes them unusually sensitive to stellar feedback. A large galaxy has a deep gravitational well. Gas heated by supernovae may be pushed away from the disk, but still remain gravitationally bound. A dwarf galaxy has much less gravitational pull. If several massive stars explode within a relatively short period, the combined energy can heat and accelerate large amounts of gas. Some of that material may be pushed into the outer halo. Some may escape entirely. This means a handful of energetic stellar events can alter the future of a small galaxy far more dramatically than they would affect the Milky Way. The early universe provided another challenge. During cosmic reionization, ultraviolet radiation spread through intergalactic space and heated much of the surrounding gas. In the smallest dark matter halos, gravity may not have been strong enough to hold on to this heated material efficiently. Gas could be prevented from falling inward or could be driven outward before many stars had time to form. As a result, some small halos may have remained almost completely dark. This connects to a long-standing puzzle known as the missing satellites problem. Computer simulations based on cold dark matter predict that a galaxy-sized dark matter halo should contain large numbers of smaller superhalos. Historically, astronomers observed far fewer luminous satellite galaxies around the Milky Way than the number of superhalos appearing in simulations. At first, this seemed like a serious disagreement. The situation has become more subtle. Modern surveys have discovered many extremely faint satellite galaxies that earlier telescopes simply could not detect. Some contain so few stars that identifying them against the foreground population of the Milky Way is difficult. At the same time, theorists recognize that a dark matter superhalo does not automatically have to contain a visible galaxy. Reionization, stellar feedback, and inefficient gas cooling can prevent stars from forming in the smallest halos. So many superhalos may exist while remaining almost completely dark. Around the Milky Way, two of the most prominent dwarf companions are the Large Magellanic Cloud and the Small Magellanic Cloud. They are not merely passive satellites. Their gravity affects the Milky Way. They interact with one another, and large quantities of gas associated with them stretch across the sky in structures such as the Magellanic Stream. The Large Magellanic Cloud is massive enough that its gravitational influence has to be considered when astronomers model the motion of the Milky Way itself. Other dwarf galaxies have suffered far more destructive encounters. A satellite passing close to a larger galaxy experiences tidal forces. The side nearest the larger galaxy feels a slightly stronger gravitational pull than the far side. Over repeated orbits, this difference can stretch the dwarf. Its outer stars can be stripped away. Gas can be removed. Eventually, the original galaxy may become so disrupted that it no longer survives as a recognizable object. The stars do not disappear. They spread into long tidal streams. These faint ribbons can wrap around the larger galaxy, preserving evidence of an object that was once independent. Over time, the streams become more dispersed, and their stars join the host galaxy's halo. In this way, small galaxies help build large ones even while being destroyed. Some survive for billions of years, some are transformed, others are swallowed almost completely. And once this process is scaled up, the distinction between a small satellite being absorbed and two major galaxies colliding begins to disappear. Gravity does not care whether the encounter looks gentle from a distance. Given enough time, it can reshape both galaxies involved. When two galaxies collide, the first thing to remove from the imagination is the idea of billions of stars smashing directly into one another. That is almost never what happens. Stars are so widely separated that even when two entire galaxies pass through each other, most individual stars simply continue moving through enormous regions of empty space. The scale can be difficult to picture. A star may be only a few million kilometers across, yet the distance to its nearest neighbor can be tens of trillions of kilometers. So a galactic collision is not really a crash in the ordinary sense. It is an enormous gravitational interaction. Dark matter halos overlap, stellar populations move through one another, gas reservoirs collide and compress. Dust is disturbed. Magnetic fields become tangled, and somewhere near the centres of the galaxies, supermassive black holes continue moving with the galactic cores that contain them. The most dramatic visible effects are often produced by tidal forces. Gravity does not pull equally on every part of a galaxy. The side nearest the approaching galaxy experiences a slightly stronger attraction than the side farther away. Across a structure tens of thousands of light-years wide, that difference becomes significant. Stars and gas can be stretched into long tidal tails. Material can form bridges between the two galaxies. Some encounters produce shells, loops, rings, and streams extending far beyond the original disks. These structures can persist for hundreds of millions of years, preserving the memory of a close encounter long after the galaxies themselves have changed shape. Yet the galaxies do not normally meet once and then immediately settle together. They can pass one another several times. After the first close encounter, gravity may carry them apart again before drawing them back. One process that gradually reduces their separation is dynamical friction. Subramanian Chandrasekhar developed an influential mathematical treatment of this effect. As a galaxy moves through surrounding stars and dark matter, its gravity disturbs that material. A slightly denser wake develops behind the moving galaxy. The gravitational pull of that wake acts back on the galaxy, causing it to lose some orbital energy and momentum. Very gradually its orbit shrinks. Each close passage can bring the galactic centers nearer until the two systems finally combine. The outcome depends greatly on the relative sizes of the galaxies. A major merger involves galaxies with broadly comparable masses. Neither system can simply ignore the other. Their disks may be heavily distorted or destroyed, their stellar orbits rearranged, and their final structure may look completely different from either original galaxy. A minor merger is more unequal. A large galaxy absorbs a substantially smaller companion. The smaller system may be stretched apart, stripped of stars and gas, and gradually incorporated into the larger galaxy, while the main structure of the larger system survives more recognizably. Gas behaves very differently from stars during these encounters. Stars usually pass one another without contact. Gas clouds can collide directly. They can shock, compress, and lose orbital energy. Gravitational torques can also remove angular momentum from the gas, allowing it to flow inward toward the central regions of the merging system. Under the right conditions, this can create a starburst. A starburst is a period of unusually intense star formation. Large quantities of gas become concentrated into dense clouds, and stars begin forming much more rapidly than they did before the interaction. Some merging galaxies can produce enormous numbers of new stars during these episodes. But this is not an automatic result of every merger. The amount of available gas matters. So does the angle of the encounter. The speeds of the galaxies matter. The timing of close passages matters. And stellar feedback can heat or disperse the same gas that the merger has compressed. Two superficially similar encounters can therefore produce very different amounts of star formation. During the 20th century, Alar Toomre and Juri Toomre demonstrated just how powerful tidal gravity could be. Using early computer models, they showed that gravitational encounters between galaxies could naturally produce long tails and bridges resembling structures already seen in observations. This helped establish the idea that many unusually shaped galaxies were not strange isolated objects at all. They were galaxies caught during interactions. Later computer simulations by Joshua Barnes and Lars Hörnquist explored the process in much greater detail. Their work helped show how mergers can redistribute stars, disturb disks, drive gas toward galactic centers, and eventually produce very different final structures. One of the clearest real examples is the antennae galaxies. They are a pair of galaxies undergoing a major interaction. Long tidal tails extend outward from the system, while regions inside the overlapping galaxies contain intense star formation. Large clouds of gas have been disturbed and compressed, producing bright clusters of young stars. The name comes from the enormous curved tails that stretch away like antennae. The entire transformation is slow by human standards. A merger can unfold over hundreds of millions of years. In some cases, the process may continue for 1 billion years or more. The galaxies approach, they make a close passage, their shapes distort, they separate. Then gravity draws them together again. Eventually, the central regions can combine, and the resulting galaxy begins settling into a new gravitational arrangement. But even then, not everything ends up neatly contained in the center. Some stars have been thrown into extremely wide orbits, others remain in streams. Smaller satellites may have been disrupted along the way. Tidal debris can drift through the outskirts for billions of years. The remnant therefore carries visible evidence of the collision long after the main event has quietened. In the faint outer regions of large galaxies, astronomers can sometimes find stars that once belonged to entirely different systems. They are the scattered remains of galaxies that came too close, were pulled apart, and slowly became part of something larger. Large galaxies do not grow only by gathering gas or merging with systems of similar size. They also grow by slowly consuming smaller neighbours. Astronomers sometimes call this galactic cannibalism. The phrase sounds rather dramatic, but the process itself is a normal part of hierarchical galaxy formation. In a universe where small structures tend to form first and larger systems assemble gradually, it is expected that many dwarf galaxies and other satellites will eventually be absorbed into more massive hosts. The process can take billions of years. A small satellite galaxy may begin by orbiting far out inside the much larger dark matter halo of its host. At first, that orbit may be wide and relatively stable, but as the satellite moves through the surrounding stars and dark matter, it creates a gravitational wake behind itself. That wake pulls backward on the satellite. This is dynamical friction. Gradually, the satellite transfers orbital energy and momentum to the surrounding material. Its orbit shrinks. Instead of circling forever at the same distance, it slowly spirals inward. As it approaches the inner regions of the larger galaxy, another process becomes increasingly important. Tidal stripping begins removing the satellite from the outside inward. The side of the satellite closest to the host feels a slightly stronger gravitational pull than the side farther away. If that difference becomes large enough, material at the outskirts of the satellite is no longer held securely. Dark matter is often stripped first because its halo extends far beyond the visible stars. Gas can also be removed. Globular clusters may be pulled away. Eventually, stars themselves begin escaping. Those stars do not simply scatter randomly through space. they continue moving on orbits related to the orbit of their original galaxy. As a result, they can form long, narrow structures known as stellar streams. A stellar stream may stretch for tens of thousands of light-years, wrapping around the host galaxy like a faint ribbon. The original satellite may still survive at one point along the stream, while material lost during earlier passages extends far ahead of it and far behind. Over time, even these streams begin to fade. Stars within them have slightly different orbital energies and slightly different periods. Some gradually move ahead, others fall behind. The once narrow structure spreads through a process known as phase mixing. Eventually, the stream becomes so dispersed that it may be difficult to identify as the remains of one particular galaxy. The stars are still there. They have simply become part of the diffuse stellar halo of the larger system. The Milky Way is doing this now. One of the clearest examples involves the Sagittarius dwarf spheroidal galaxy. This small galaxy has been orbiting the Milky Way and repeatedly passing through regions where the galaxy's tidal gravity is strong enough to pull it apart. Its original structure has been heavily disrupted. Stars removed from it form the enormous Sagittarius stream, which wraps around the Milky Way. By studying the positions and motions of those stars, astronomers can reconstruct parts of the dwarf galaxy's orbit and estimate how the Milky Way's gravity has affected it. In a sense, the Milky Way is carrying the remains of earlier meals around its outskirts, and those remains are extremely useful. The attempt to reconstruct a galaxy's history from the stars it contains is known as galactic archaeology. Instead of digging through layers of rock, astronomers examine stellar ages, motions, orbits, and chemical compositions. A star can retain information about where it formed long after its original galaxy has disappeared. Stars born together tend to begin with related chemical compositions because they formed from the same broad reservoir of gas. Astronomers can compare the relative abundances of elements such as iron, magnesium, calcium, and other products of stellar nucleosynthesis. This approach is often described as chemical tagging. If a group of stars shares an unusual pattern of elemental abundances as well as related motions, that combination can suggest that they once belonged to the same smaller galaxy or star-forming environment. It is not always possible to reconstruct every lost system neatly. Billions of years of mixing can make the evidence extremely subtle, but chemistry provides another clue that gravity alone cannot erase easily. Globular clusters can preserve similar information. These are dense, roughly spherical collections of old stars, sometimes containing hundreds of thousands of members. Some globular clusters formed within the main body of a large galaxy. Others appear to have formed inside smaller galaxies that were later absorbed. When the parent galaxy is destroyed, the globular cluster can survive as a compact object orbiting its new host. Its age, chemistry, and motion may then reveal that it did not originate where it is found today. Galactic cannibalism operates on much larger scales as well. At the centers of galaxy groups and clusters, giant galaxies can grow through repeated mergers with surrounding companions. Over billions of years, smaller galaxies lose orbital energy, spiral inward, and contribute stars to the central system. Not every stripped star becomes part of one galaxy. In rich clusters, some stars are pulled so far from their original hosts that they end up orbiting within the gravitational potential of the cluster itself. This produces intracluster light. It is an extremely faint glow spread through the spaces between galaxies, created by stars that no longer belong clearly to any single one. These wandering stars are another record of past interactions. The outer regions of galaxies and clusters are therefore full of archaeological evidence. Streams, shells, diffuse halos, scattered globular clusters, faint structures that can contain the remains of systems destroyed billions of years ago. Observing them is difficult because their surface brightness can be extraordinarily low. Future surveys are designed to search for these features in greater detail. The European Space Agency mission Arrakis is intended to study faint stellar halos and streams around nearby galaxies, helping astronomers trace the signatures of past mergers and compare them with predictions from modern galaxy formation models. The deeper astronomers look into these dim outskirts, the less isolated galaxies appear. A smooth halo can hide the remains of many smaller systems. A faint stream may be the stretched remains of a dwarf galaxy. A globular cluster may have crossed intergalactic space as part of another galaxy before becoming part of its present host. Large galaxies are built partly from this accumulation of forgotten structures. But while some of the clearest evidence of their past lies far out in the halo, another important part of their evolution takes place in precisely the opposite direction. At the very centre of most large galaxies sits a supermassive black hole. It occupies a tiny region compared with the galaxy around it. Yet when matter begins falling toward that black hole, the energy released can influence gas on scales vastly larger than the black hole itself. And that makes the quiet centre of a galaxy capable, at times, of becoming one of its most powerful engines of change. At the centres of most large galaxies, astronomers find something extraordinary: a supermassive black hole. These objects can contain millions, hundreds of millions, or even many billions of times the mass of the Sun. They are found in spiral galaxies, elliptical galaxies, and many systems in between, suggesting that the growth of large galaxies and the growth of their central black holes are deeply connected. Yet the black hole itself occupies an almost absurdly small region compared with the galaxy around it. Its event horizon may span a distance comparable to the scale of a planetary system, while the galaxy can extend for tens or hundreds of thousands of light years. The black hole does not directly control the orbit of every star. Far from the centre, the combined gravity of stars, gas, dark matter, and the rest of the galaxy is far more important. The direct gravitational dominance of the black hole is usually confined to the central region. So how can something so compact influence an entire galaxy? The answer lies not simply in gravity, but in what happens when matter falls toward the black hole. Gas approaching a supermassive black hole rarely falls straight in. It normally carries angular momentum and begins orbiting, forming a flattened structure called an accretion disk. As material in the disk moves inward, friction, magnetic processes, and turbulence convert gravitational energy into heat. The gas can become extraordinarily hot. Before the material finally crosses the event horizon, it may release enormous amounts of energy as visible light, ultraviolet radiation, X-rays, and other forms of electromagnetic radiation. When this process becomes powerful enough, the bright central region is known as an active galactic nucleus. The black hole itself remains dark. The light comes from material outside it. Some active galactic nuclei can outshine the combined stars of their host galaxies. They may also produce powerful winds that rush away from the central region. In certain systems, magnetic fields help launch narrow jets of particles travelling at speeds close to the speed of light. These relativistic jets can extend thousands or even millions of light years beyond the galaxy itself. Among the most luminous active galactic nuclei are quasars. Quasars were far more common when the universe was younger. Several billion years after the Big Bang, galaxies generally contained more cold gas than many large galaxies do today, and interactions between galaxies were more frequent. Under the right circumstances, large quantities of material could reach central regions and feed rapidly growing supermassive black holes. The resulting quasar could shine across billions of light years. Getting gas from the outer regions of a galaxy all the way toward a black hole is not simple. Gas orbiting within a disk has angular momentum, so something must disturb that motion. Major mergers can drive gas inward. Minor interactions can also contribute. A galactic bar can exert gravitational torques that rearrange gas orbits. Instabilities within a disk may move material toward the center. Turbulence, collisions between gas clouds, and smaller-scale gravitational processes can continue the journey. There is no single pathway that explains every active galactic nucleus. Different galaxies can feed their central black holes in different ways. Once the black hole becomes active, the energy released can begin affecting the surrounding galaxy. This is known as active galactic nucleus feedback. One form is often described as radiative, or quasar mode, feedback during a highly luminous phase. Intense radiation and fast winds from the region around the black hole can heat surrounding gas or push it outward. If enough cold gas is disrupted or expelled, the amount available for future star formation can decrease. Another form is commonly called mechanical, or radio mode, feedback. This is especially important when jets from the central black hole interact with hot gas in the surrounding halo or galaxy cluster. The jets can inflate enormous cavities and inject energy into the gas. That extra energy can prevent the gas from cooling efficiently, and if hot halo gas cannot cool, it cannot easily sink toward the galaxy and replenish the cold material from which new stars form. In this way, a black hole can influence regions vastly larger than its event horizon. It does not need to pull every star around directly. Instead, it changes the behavior of the gas. Radiation can heat it, winds can move it, jets can stir it, outflows can remove it, and preventing hot gas from cooling can gradually cut off the supply needed for continued star formation. This feedback has become an important ingredient in modern simulations of galaxy formation. Without some mechanism for regulating cooling and star formation, computer models can produce massive galaxies that form too many stars and remain too active for too long. But modelling active galactic nucleus feedback is extremely difficult. The immediate environment around a supermassive black hole may be smaller than a light year in some important respects. The surrounding galaxy spans tens of thousands of light years. Its dark matter halo can extend hundreds of thousands of light years farther. A simulation must somehow connect processes occurring near the black hole with consequences spread across an enormous range of scales. Many details therefore remain uncertain. Astronomers also see intriguing relationships between supermassive black holes and the galaxies containing them. One of the best known connects the mass of a black hole with the stellar velocity dispersion of the galactic bulge. Galaxies with more massive central bulges and faster random stellar motions tend to host more massive black holes. This suggests some form of linked growth. Perhaps black hole feedback regulates the surrounding bulge. Perhaps the same supply of gas and the same merger history help build both. Perhaps several processes contribute. The correlation is real, but the complete direction of cause and effect is still being investigated. Our own Milky Way contains a supermassive black hole known as Sagittarius A star. It has a mass of roughly 4 million suns. Today it is comparatively quiet. Only modest amounts of material are currently falling toward it, so it is nothing like the brilliant quasars observed in the distant universe. But evidence suggests that Sagittarius A star has experienced more active periods in the past. The giant structures known as the Fermi bubbles. Extending far above and below the galactic center, may preserve evidence of energetic activity from the central region, although the exact history of their formation continues to be studied. So even a galaxy that seems calm today may have contained a much more energetic centre in the past. A supermassive black hole can spend long periods almost dormant, then become active when new material reaches it. And during those active phases, it can help determine whether surrounding gas cools, escapes, or remains available to make stars. That brings us to one of the central questions in the life of a galaxy. A galaxy can spend billions of years acquiring gas and building new generations of stars. But eventually, many large galaxies become quiet. Their bright young stars disappear. Their cold gas reservoirs decline. Star formation slows to a faint trickle. The galaxy still exists and still shines, but in an important sense, its most creative period is over. The question is what finally causes that change. A galaxy can continue shining long after it has stopped making many new stars. That distinction is important. When astronomers describe a galaxy as dead, passive, or quenched, they do not mean that every star has gone dark. Existing stars can continue shining for billions of years. Some will swell into red giants, some will shed their outer layers, and some will eventually become white dwarfs, neutron stars, or black holes. What has changed is the rate at which new stars are being created. A substantial and sustained decline in star formation is known as quenching. For star formation to continue, a galaxy needs a supply of cold, dense molecular gas. If that supply is reduced, heated, dispersed, or stabilized against collapse, the production of new stars can slow dramatically. The change is often visible in the overall color of a galaxy. Actively star-forming galaxies tend to contain many hot, massive, short-lived stars. These stars shine strongly at blue and ultraviolet wavelengths, giving the galaxy a relatively blue appearance. A passive galaxy contains far fewer of these young stars. Its light is dominated more strongly by older, cooler stellar populations, making it appear redder. This creates a useful broad pattern. When astronomers compare galaxy color, stellar mass, and star formation activity, many actively star-forming systems gather in a region known as the blue cloud. Passive galaxies tend to occupy another region known as the red sequence. Between them lies the green valley. Galaxies found there often have intermediate colors and reduced star formation, making the green valley a useful place to search for systems that may be moving from an active state toward a quieter one. The picture is not perfectly tidy. Dust can absorb blue and ultraviolet light, making an actively star-forming galaxy appear redder than it really is. Astronomers therefore use more than color alone when deciding whether a galaxy is truly passive. Spectra, infrared emission, gas measurements, and other indicators of recent star formation help reveal what is actually happening. One of the simplest ways for a galaxy to become quiet is gas exhaustion. Every generation of stars consumes some of the cold molecular gas available within the galaxy. If that gas is not replaced quickly enough, the reservoir gradually declines. The galaxy does not suddenly stop. Star formation simply becomes harder to sustain. A related process is known as starvation or strangulation. A galaxy may still contain cold gas in its disk, but the larger supply feeding it from the surrounding halo or cosmic web can be reduced. Without fresh material arriving, the galaxy begins living on what it already has. Stars continue to form for a while. The remaining gas is gradually consumed, heated or expelled. Over time, the star formation rate falls. Another possibility is halo quenching. In a sufficiently massive dark matter halo, infalling gas can be heated to very high temperatures. Instead of remaining cool enough to flow efficiently toward the galactic disk, it can form an extended hot atmosphere around the galaxy. If that gas cannot radiate energy away quickly enough, it remains suspended in the halo rather than settling inward. The galaxy may therefore be surrounded by plenty of material while still lacking the cold, dense gas required to produce new stars. Feedback can make this situation even more effective. Massive stars and supernova explosions inject energy into surrounding gas. In lower mass galaxies, these processes can push material outward or even remove it from the system. In more massive galaxies, activity around a central supermassive black hole may become especially important. Radiation, winds, and relativistic jets produced by an active galactic nucleus can heat gas, disturb it, or prevent hot halo material from cooling efficiently. The central black hole does not need to empty the entire galaxy in one dramatic event. It may be enough to make the supply of star-forming gas progressively harder to maintain. There is also a more subtle possibility. A galaxy can sometimes retain gas without forming stars efficiently. This leads to an idea known as morphological quenching. Marie Martig and collaborators explored how the internal structure of a galaxy can affect the stability of its gas. If a galaxy develops a massive central bulge, the gravitational environment of the disk can change. The gas may remain present, but the disk can become more resistant to the gravitational instabilities that normally cause dense clouds to collapse. In other words, a galaxy can have fuel without being able to use it effectively. The presence of gas alone is therefore not enough. The gas must be cold enough, it must be dense enough. It must be arranged in a way that allows gravity to overcome pressure, turbulence, magnetic effects, and large-scale orbital stability. A reservoir that fails those conditions may remain relatively inactive. This helps explain why there is no single universal mechanism responsible for quenching. Different galaxies can become quiet for different reasons. A dwarf galaxy may lose gas through stellar feedback. A massive galaxy may struggle to cool the hot atmosphere surrounding it. Another may experience strong active galactic nucleus feedback. Some may simply consume their available gas more quickly than it can be replaced. Others may be stabilized by their internal structure. And several of these processes can operate together. There are also galaxies that appear to have stopped forming stars unusually quickly. These are often called post-starburst galaxies. Their spectra contain the signatures of large numbers of stars formed during a relatively recent burst, but they show much less evidence of ongoing star formation. They are therefore caught in an interesting transitional state. A strong episode of star formation has recently ended, but the stellar population has not yet had enough time to age into the appearance of a completely passive galaxy. Post-starburst systems can provide clues about rapid quenching mechanisms, including mergers, gas depletion, and energetic feedback. Even so, galactic death is not always permanent. A quenched galaxy may later acquire fresh gas. A merger can introduce new material. Gas already present in the halo may eventually cool. An interaction can compress material that had previously remained stable. Under the right conditions, limited star formation can begin again. This is sometimes described as rejuvenation. So the life of a galaxy does not necessarily follow one clean path from blue to red, active to passive, and then remain there forever. Some fade slowly, some change rapidly, some pause, some begin forming stars again. And while many of the mechanisms responsible for quenching operate within the galaxy or its surrounding halo, there is another powerful influence that depends almost entirely on location. A galaxy drifting through a relatively quiet region of space experiences one kind of life. A galaxy plunging into a crowded group or massive cluster experiences something very different. There, the environment itself can begin stripping, heating, disturbing, and reshaping the galaxy. And sometimes the neighbourhood becomes just as important as anything happening inside it. Galaxies do not evolve in isolation. Some spend much of their lives in relatively quiet surroundings, while others become members of galaxy groups and clusters, where the environment can gradually reshape almost every part of them. A galaxy group is a collection of galaxies held together within a larger shared gravitational structure. Our own local group is one example. It contains the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of smaller systems, with the Milky Way and Andromeda providing much of the group's visible mass. On larger scales are galaxy clusters. A rich cluster can contain hundreds or even thousands of galaxies moving within an enormous shared dark matter halo. The space between those galaxies is not empty. Much of a massive cluster is filled with extremely hot, extremely thin gas, known as the intracluster medium. This material can reach temperatures of tens of millions of degrees and shines strongly at X-ray wavelengths. Although the gas is vastly thinner than any atmosphere we experience on Earth, a galaxy moving quickly through it can still feel its effects. One of the most important is ram pressure stripping. James Gunn and Richard Gott described how gas inside a galaxy can be pushed away as the galaxy moves through the surrounding intracluster medium. A rough comparison is the pressure felt by an object moving through air. The analogy has limits, because cluster gas is incredibly diffuse, but the basic principle is similar. A galaxy travelling through that gas at hundreds or even more than 1,000 kilometers per second experiences a continuous pressure against its own interstellar material. Stars are largely unaffected because they are compact and interact mainly through gravity. Gas is much easier to move. If the ram pressure becomes strong enough, cold gas can be stripped out of the galactic disk. That matters because cold gas is the raw material for new stars. Remove enough of it, and star formation eventually declines. Some of the most striking examples are jellyfish galaxies. These systems appear to trail long streams of gas behind them as they move through a cluster. The strip material can extend for tens of thousands of light years. In some cases, dense regions inside those tails continue forming stars even after the gas has left the main body of the galaxy. For a time, the galaxy can look as though it is leaving pieces of itself behind. Gas stripping is only one environmental effect. Gravity also becomes more complicated inside a crowded cluster. A galaxy feels the pull of the cluster as a whole. If that gravitational field changes noticeably across the width of the galaxy, tidal forces can remove loosely bound stars, gas and dark matter from its outskirts. Nearby galaxies can create additional disturbances during close passages. Many cluster encounters happen too quickly for two galaxies to merge immediately. Instead, a smaller galaxy may experience repeated fast flybys over billions of years. The cumulative effect is known as galaxy harassment. Each encounter may only provide a modest gravitational disturbance, but repeated encounters can gradually alter stellar orbits, thicken a disk, stretch its shape, and remove material from the outer regions. A delicate spiral galaxy can become noticeably less delicate after enough of these visits. Another quieter mechanism is environmental strangulation. Before entering a group or cluster, a galaxy may possess an extended reservoir of halo gas capable of cooling and replenishing its disk. Once the galaxy falls into a denser environment, that outer gas can be stripped or prevented from remaining bound. The cold gas already inside the disk may survive for some time. Stars continue forming. but the replacement supply has been cut off. Gradually, the galaxy consumes what remains and becomes quieter. This transformation can begin even before a galaxy reaches a massive cluster. Many clusters grow by absorbing entire smaller galaxy groups. A galaxy inside one of those groups may already have undergone interactions, gas loss, or reduced star formation before the group itself falls into the larger cluster. Astronomers call this preprocessing. It means that when a changed galaxy is finally observed inside a cluster, not all of the transformation necessarily happened there. Part of the story may belong to an earlier environment. Cluster conditions do not always suppress star formation immediately. Sometimes they can briefly do the opposite. Pressure from surrounding gas can compress a galaxy's own interstellar material. Gravitational encounters can disturb gas clouds. Under the right conditions, that compression can temporarily increase star formation. The outcome depends on the galaxy's mass, how much gas it contains, the path it follows through the cluster, the speed of the encounter, and how strongly feedback responds afterward. A galaxy may therefore experience a short burst of activity before losing enough gas for star formation to decline. Over longer periods, these environmental processes help explain an important pattern. Dense cluster cores contain a relatively high proportion of elliptical and lenticular galaxies. Actively star-forming spirals are more common in less crowded surroundings and toward the outskirts of clusters. Environment is not the only explanation for this difference, but it clearly plays an important role. Gas can be removed. Disks can be heated. Small systems can be disturbed repeatedly. Mergers can alter structure. And the supply of fresh material can be quietly cut off. The appearance of a galaxy therefore reflects not only what has happened inside it, but also where it has spent its life. This is one of the recurring themes of galactic evolution. Every galaxy carries evidence of its surroundings, and nowhere is that easier to appreciate than in the galaxy we inhabit. The Milky Way may look like one coherent spiral system today, but its stars preserve the remains of earlier encounters, absorbed companions, ancient mergers, and structures that formed long before the present disk took shape. By reading those stellar motions and chemical signatures carefully, astronomers can begin reconstructing how our own galaxy was assembled. The Milky Way may look like one enormous, coherent galaxy today, but it did not begin that way. What we see around us is the result of more than 13 billion years of growth. Gas has fallen inward from the surrounding cosmic web. Generations of stars have formed, aged, and died. The galactic disk has been disturbed and reshaped. Smaller galaxies have approached, been stretched apart, and gradually absorbed. Internal structures such as the central bar have developed and changed. The Milky Way is therefore not one ancient object that appeared early in cosmic history and remained essentially unchanged. It is an accumulation of many histories. Even its present structure reflects this complexity. Most familiar stars, including the Sun, belong to the galactic disk. Within that disk is a relatively thin component containing much of the cold gas, dust, and ongoing star formation. The Sun lies inside this thin disk, roughly 26,000 light-years from the galactic center. Surrounding it is a thicker stellar component known as the thick disk. Its stars generally extend farther above and below the galactic plane, tend to be older on average, and follow somewhat less orderly orbits than stars in the thin disk. Near the center lies a dense bulge crossed by the Milky Way's elongated stellar bar. Far beyond the bright disk stretches a much fainter stellar halo. The halo contains old stars, globular clusters, and streams produced by disrupted satellite galaxies. An even larger gaseous halo surrounds the galaxy, containing hot and cooler material that can circulate between the Milky Way and its surroundings. Beyond all of this lies the much more extensive dark matter halo, which provides most of the galaxy's mass and extends far beyond the region filled with visible stars. The Milky Way also has a population of satellite galaxies orbiting within this larger gravitational structure. Some are relatively substantial, others contain remarkably few stars. Together, these components preserve different parts of the galaxy's past. The oldest stars are particularly valuable. Ancient stars in the stellar halo and central regions formed before the modern thin disk had taken its present form. Their chemical compositions preserve clues about the gas from which they were born. Their motions can reveal whether they formed inside the early Milky Way or arrived later as part of another galaxy. This is where galactic archaeology becomes especially powerful. One of the most important tools in that work has been the European Space Agency's Gaia mission. Gaia measured the positions and motions of enormous numbers of stars with extraordinary precision. It determined how stars move across the sky through proper motion, helped estimate their distances, and supplied radial velocity measurements for many stars showing movement toward or away from us. When these measurements are combined, astronomers can reconstruct stellar motion through three-dimensional space. That turns the Milky Way into something rather like an enormous archaeological site in motion. Stars that appear scattered across the sky today may share related orbits. They may possess similar chemical compositions, and together those clues can reveal structures left behind by mergers that happened billions of years ago. One of the most striking examples is known as Gaia sausage Enceladus. The unusual name refers to a large population of stars thought to be debris from a substantial galaxy that merged with the early Milky Way. The word sausage comes from the elongated shape made by these stars when their velocities are plotted in a particular way. Their motions are highly radial, meaning many travel on stretched orbits carrying them inward and outward through the galactic halo rather than simply circling the centre. Enceladus was added as another name for the same broad ancient merger event. Amina Helmi and collaborators played an important role in identifying coherent stellar motions and chemical evidence associated with this major accreted population. The progenitor galaxy appears to have been substantial, though still much smaller than the Milky Way today. Its merger occurred several billion years after the Big Bang, when our galaxy was still developing. The collision contributed stars to the halo and may also have strongly influenced the structure of the early galactic disk. But Gaia sausage Enceladus is not the entire story. Astronomers have identified many other streams, clumps, globular cluster associations, and possible merger remnants. Some are confidently linked to known satellite galaxies, others remain debated. Part of the difficulty is that ancient debris becomes mixed over time. Stars that once belonged to one compact system can eventually spread across enormous regions of the halo. Different merger events may overlap, and structures created internally within the Milky Way can sometimes resemble signatures of accreted material. The history is therefore more like a heavily edited manuscript than a perfectly preserved diary. The thick disk provides another example of this complexity. It contains older stars extending farther above and below the galactic plane than the thin disk. One possibility is that ancient mergers heated an earlier stellar disk, increasing the random vertical motions of its stars. But this is probably not the only process involved. Some thick disk stars may have formed naturally within a turbulent early Milky Way, when the galaxy contained more gas and the young disk itself was thicker. Radial migration may also have rearranged stellar populations over time. The thick disk may therefore preserve several overlapping episodes of galactic evolution rather than one single dramatic event. and the process of disruption and absorption has not ended. The Sagittarius dwarf spheroidal galaxy is currently being torn apart by the Milky Way. Its repeated passages through the galactic gravitational field have stripped away enormous numbers of stars. Those stars now form the Sagittarius stream, a broad structure wrapping around the galaxy. The interaction has probably influenced the Milky Way's disk as well, helping create ripples and disturbances that can still be detected in stellar motions. Another important neighbour is the Large Magellanic Cloud. For many years it was often treated as a relatively modest satellite, but modern measurements indicate that it may be considerably more massive than once thought. It may also have entered the Milky Way's immediate neighbourhood comparatively recently in cosmic terms. Because of that large mass, the Large Magellanic Cloud does not simply orbit as a tiny object around an immovable Milky Way. Its gravity pulls on the Milky Way in return. It affects estimates of the galaxy's motion, disturbs the dark matter halo, influences other satellites, and must be included when astronomers calculate the future dynamics of the local group. So even now, the Milky Way remains unfinished. Cold gas still forms stars inside the disk. Supernovae send material into the halo. Some gas later returns. The central bar rearranges stellar and gaseous orbits. Satellite galaxies continue to interact with the disk and halo. External material is still being added. Old merger debris continues to mix into the galaxy. What looks like a stable spiral from the inside is actually a structure still evolving on many different timescales. And the Milky Way is not alone. Across roughly 2.5 million light-years of intergalactic space lies Andromeda, another enormous spiral galaxy and the other dominant member of the local group. For many years, the future of these two galaxies was described in almost inevitable terms. They were approaching one another. Gravity would bring them together. Their disks would collide. Eventually, the two would merge into a single larger galaxy. But the future of a system this complicated depends on more than knowing that two large galaxies are moving toward each other. Their sideways motions matter. Their total masses matter. The Large Magellanic Cloud matters. The Triangulum Galaxy matters. And once all of those uncertainties are included, a question that once appeared almost settled becomes much more interesting. Are the Milky Way and Andromeda truly destined to collide at all? Andromeda is the nearest large spiral galaxy to the Milky Way. It lies roughly 2.5 million light-years away, close enough to be visible to the naked eye under sufficiently dark skies as a faint, misty patch of light. What we see is the combined glow of hundreds of billions of stars. And Andromeda is approaching us. Measurements of its motion along our line of sight show that the separation between the Milky Way and Andromeda is decreasing. For many years, this fact led to one of the most familiar predictions about the distant future of our galaxy. In roughly 4 to 5 billion years, the Milky Way and Andromeda would collide. The two great spiral galaxies would pass through one another, become gravitationally entangled, make several further close approaches, and eventually merge into one larger system. It became such a familiar prediction that it was often presented almost as a certainty, but predicting the motion of galaxies over billions of years is more difficult than knowing whether one of them is currently approaching us. The crucial uncertainty involves sideways motion. Imagine watching an object approaching from a very great distance. If it is travelling directly toward you, its path may eventually cross your position. But if it also has enough sideways velocity, it may pass safely to one side. The same principle applies to galaxies, although the scale is rather more impressive. Andromeda's motion toward the Milky Way is comparatively straightforward to measure because it changes the wavelengths of its light through the Doppler effect. its sideways motion across the sky is much harder to determine. At a distance of roughly 2.5 million light-years, even a substantial sideways speed produces an extremely tiny apparent movement. Yet that small motion can make an enormous difference after several billion years. If Andromeda's trajectory is sufficiently direct, the galaxies can experience a close encounter and perhaps merge. If its tangential motion is larger, they may pass at a greater distance. And because gravity continually changes both trajectories, even a near miss could place the galaxies onto complicated future orbits. Astronomers have gradually improved these measurements. Observations from the Hubble Space Telescope have been particularly important for estimating Andromeda's motion across the sky. The European Space Agency's Gaia mission has also improved our knowledge of stellar motions throughout the local group and helped refine the gravitational picture surrounding the Milky Way. But there is another complication. The Milky Way and Andromeda are not two isolated objects floating alone in otherwise empty space. They belong to the local group. The Triangulum Galaxy is another substantial member. The Large Magellanic Cloud is smaller than the Milky Way, but massive enough for its gravity to influence calculations of the Milky Way's own motion. Every major body pulls on the others, so predicting the future becomes a many-body gravitational problem. Change the estimated mass of the Large Magellanic Cloud, and the motion of the Milky Way changes slightly. Change the trajectory of the Triangulum Galaxy, and the gravitational history of Andromeda can change. Alter the mass of either large dark matter halo, and the strength of future interactions changes again. Small uncertainties today can become very large differences when projected across billions of years. This became particularly clear in an analysis published in 2025. Till Sowler, Jehan Delamel, Ruby Wright and collaborators modelled the future of the local group while including uncertainties in the masses, positions and motions of the major galaxies. Instead of calculating one idealized future, they explored many possible futures consistent with the measurements. The result was very different from the old picture of an unavoidable collision. Their analysis found close to a 50% probability that the Milky Way and Andromeda will not merge at all during the next 10 billion years. That does not mean the old predictions were foolish. They were based on the best measurements and models available at the time. What changed was the amount of information included and the treatment of uncertainty. The future is now better described as genuinely uncertain. A merger remains entirely possible. A close passage remains possible. And improved measurements of Andromeda, the Large Magellanic Cloud, the Triangulum Galaxy, and the dark matter halos surrounding them may shift the probabilities again. Astronomy occasionally provides the comforting reminder that even a prediction involving the destruction of our entire galactic structure can become less certain with better paperwork. If a Milky Way and Andromeda merger does occur, however, it would be spectacular on galactic scales. As the galaxies approached, their enormous dark matter halos would interact first. Tidal forces would begin distorting the stellar disks. Spiral arms could be stretched and disrupted. Long streams of stars and gas might be pulled outward into tidal tails. Other material could form bridges between the galaxies. The disks themselves could become warped. During a close passage, stars from the Milky Way and Andromeda would move through overlapping regions of space. Yet direct collisions between individual stars would remain extraordinarily unlikely. Even in the crowded disk of a galaxy, stars are separated by immense distances. The solar system would therefore be very unlikely to experience another star crashing directly through it. Its position within the galaxy could still change dramatically. Gravitational disturbances during the merger could alter the Sun's orbit, perhaps moving the solar system much farther from the centre of the eventual remnant. Other stars could be thrown onto wider orbits or into the extended halo. Some could even become unbound. Gas would experience a more turbulent fate. Unlike stars, clouds of interstellar gas can collide and compress. Gravitational torques could drive some material inward. Under the right conditions, compressed gas might produce episodes of enhanced star formation. But both galaxies will be several billion years older by then, so the amount of cold gas still available will strongly affect how intense any future starburst could become. After repeated passages, dynamical friction could cause the two galactic cores to lose orbital energy and move closer together. The neat spiral structures might disappear. Stars from both galaxies would become mixed into a larger gravitational system. Depending on the details of the encounter and the amount of remaining gas, the remnant could eventually resemble a large elliptical or another smoother stellar system rather than two distinct spirals. Near the centres would be another pair of objects slowly approaching one another. The Milky Way contains a supermassive black hole with a mass of roughly 4 million suns. Andromeda contains a substantially more massive central black hole. These black holes would not immediately collide when the outer galaxies first overlapped. They would initially travel with their respective galactic cores. Only after the cores themselves had merged would processes such as dynamical friction begin drawing the black holes into a tighter common system. Eventually they could form a gravitationally bound binary. Further interactions with stars and gas could continue shrinking their separation. If the two black holes ultimately merged, the final stage would release an enormous burst of gravitational waves. This would occur long after the first galactic encounter. The popular name Milkomeda is sometimes used for the imagined final product of the Milky Way and Andromeda merger. It is an informal nickname. It is not an official astronomical designation, and with the future collision itself now recognized as uncertain, it certainly should not be treated as the guaranteed name of a guaranteed future galaxy. Whether or not Milkomeda ever exists, the local group faces a much broader long-term future. The expansion of the universe is accelerating. Galaxies that are gravitationally bound within the local group can continue interacting with one another despite that expansion. But much more distant galaxies are not bound to us in the same way. Over tens and hundreds of billions of years, the distance between the local group and many other galactic systems will continue increasing. Eventually, sufficiently distant galaxies will recede so rapidly that their light becomes extraordinarily redshifted and increasingly difficult to observe. In the far future, the descendants of whatever galaxies remain gravitationally bound within the local group may inhabit what appears to be an increasingly empty universe. The great cosmic web will still exist beyond them, but much of it will effectively disappear from view. Even then, galactic evolution will not truly stop. Stars will continue aging, stellar remnants will orbit, galaxies and satellites that remain gravitationally bound may continue merging. Some stars will be lost through gravitational encounters. Gas will become increasingly scarce, black holes will remain, and the universe itself will continue expanding around whatever structures gravity manages to keep together. There is no single moment when a galaxy becomes permanently finished. The Milky Way was assembled from earlier structures and is still changing now. Andromeda has its own complicated history. Their futures remain entangled, but not predetermined. They may collide. They may pass one another. They may follow a more complicated gravitational dance lasting billions of years. Whatever happens, both galaxies will continue doing what galaxies have always done. Moving, changing, absorbing, losing, rearranging. and slowly becoming something different from what they were before. Galaxies are born by changing. They do not appear suddenly as complete spirals, ellipticals, or glowing islands of stars. Their origins are much more gradual. The first ingredients were tiny differences in density in the early universe. Those differences were almost unimaginably small, but gravity amplified them over time. Slightly denser regions attracted more matter. Their gravity strengthened. More material gathered. What began as faint irregularities eventually developed into the enormous filaments, sheets, clusters and voids of the cosmic web. Dark matter played a central role in that transformation. Long before mature galaxies existed, dark matter had already begun collecting into gravitational halos. Those halos acted as the foundations of later galaxies. Ordinary hydrogen and helium fell into them. Gas became compressed. Some of it was shock-heated, some cooled. And in sufficiently dense regions, gravity continued pulling matter inward until the first stars began to form. Those first generations of stars changed the universe around them almost immediately. They produced intense radiation. They heated surrounding gas. They ended their lives by returning material to space, and through nuclear fusion and stellar explosions, they manufactured elements heavier than the hydrogen and helium that had dominated the early universe. Carbon appeared. Oxygen appeared. Silicon, iron, and many other elements accumulated gradually across successive generations of stars. The chemistry of galaxies became richer. That chemical enrichment made later star formation easier in important ways. Dust grains could form. Gas could cool more efficiently. Molecular clouds became more chemically complex. The material that would eventually produce rocky planets was being created and recycled through stars long before any planet like Earth could exist. Meanwhile, galaxies themselves continued assembling. Gas arriving from the cosmic web carried angular momentum. Instead of falling directly into galactic centers, much of it began orbiting. As the gas cooled and redistributed angular momentum, rotating disks formed inside much larger dark matter halos. Those early disks were often turbulent and irregular. They were disturbed by incoming gas, internal instabilities, and frequent interactions with other young systems. But over time, many developed into the broad rotating structures we recognize as spiral galaxies. Even then, their shapes were never permanent. Spiral arms are dynamic patterns. Stars and gas move through them. Some arms can behave as regions of enhanced density. Others may be transient structures produced by local gravitational instabilities. Nearby companions can also pull on a disk and strengthen dramatic spiral patterns. Inside many galaxies, bars form and begin rearranging material. They can transfer angular momentum. They can guide gas towards central regions. Bulges can develop through mergers, rapid early growth, or slower internal processes. And between the familiar categories sit lenticular galaxies, systems that keep a disk and central bulge while losing much of the cold gas, an obvious spiral structure associated with active star formation. Elliptical galaxies tell another kind of history. Their stars move along a wider range of orbits rather than remaining concentrated within one thin rotating disk. Some ellipticals form through major mergers that disrupted earlier galactic structures. Others grew through repeated smaller mergers. The largest central ellipticals can continue increasing in size through relatively dry mergers, adding existing stars without producing enormous new bursts of star formation. The shape of a galaxy therefore records both internal dynamics and external experience. Two galaxies that look almost identical today may have arrived there by very different routes. One may have evolved quietly for billions of years, another may have survived repeated encounters. A third may be the combined remnant of several earlier galaxies whose separate identities have been almost completely erased. Dwarf galaxies make this especially clear. They may be small, but they are fundamental to the hierarchical picture of galaxy formation. Some remain independent today, others orbit much larger hosts. And countless earlier dwarf systems were probably torn apart and absorbed while larger galaxies were assembling. That process continues. Minor mergers gradually add stars, gas, and dark matter to larger galaxies. Major mergers can rearrange entire galactic structures. Tidal forces stretch stars into streams and tails. Dynamical friction slowly draws satellites inward. Tidal stripping removes dark matter, gas, globular clusters, and stars. Galactic cannibalism steadily turns once independent galaxies into pieces of larger ones. The resulting stellar streams can wrap around a galaxy for billions of years before gradually dispersing through phase mixing. Even after the original satellite has disappeared, its stars can remain as a faint archaeological record. So much of the visible universe has been assembled from things that no longer exist as separate objects. At the centres of most large galaxies, another important influence appears. A supermassive black hole does not command every star in its galaxy. Its direct gravitational dominance is confined to the central region. But when gas falls toward it, the situation changes dramatically. Material in an accretion disk can release enormous amounts of energy before crossing the event horizon. Radiation can heat surrounding gas. Powerful winds can drive material outward. Relativistic jets can extend far beyond the visible galaxy. Active galactic nucleus feedback can therefore influence whether gas cools, remains hot, escapes, or becomes available for future star formation. And eventually, many galaxies begin to quieten. Galactic death does not mean disappearance. The stars remain. They continue orbiting. They continue aging. What declines is the formation of new stars. This is quenching. Cold molecular gas may be exhausted faster than it can be replaced. Fresh gas from the cosmic web may be cut off. A massive halo may keep incoming material too hot to cool efficiently. Stellar feedback may remove or disperse gas. Activity around a supermassive black hole may prevent material from cooling. A central bulge can even help stabilize a gas disk against gravitational collapse. In groups and clusters, the environment provides still more ways to become quiet. Ram pressure can strip gas from a galaxy as it moves through the hot intracluster medium. Repeated encounters can heat and distort the stellar disk. Tidal forces can remove material. Strangulation can separate a galaxy from the halo gas that once replenished its cold reservoir. But even here, the word death should be used gently. Galactic quenching is not always permanent. Fresh gas can arrive later. A merger can introduce new material. An interaction can compress gas that had previously been stable. A galaxy that appeared passive can sometimes experience renewed star formation. Galactic evolution rarely respects neat beginnings and endings. The Milky Way is a particularly familiar example. It appears to us today as one barred spiral galaxy. Yet hidden within it are the remains of earlier systems. The stellar halo contains streams from disrupted satellites. Ancient stars preserve chemical evidence of different origins. Gaia Sausage Enceladus records a substantial merger from the Milky Way's distant past. The Sagittarius dwarf spheroidal galaxy is still being torn apart today. The Large Magellanic Cloud continues to tug on the Milky Way and influence its motion. Gas still circulates between the disk and halo. Stars are still forming. The central bar is still rearranging orbits. The galaxy is still being built. And beyond it lies Andromeda. For many years, the future of the Milky Way and Andromeda was described as though a merger were inevitable. A collision in roughly 4 to 5 billion years became one of the most familiar predictions in popular astronomy. That picture is now less certain. The future depends on Andromeda's sideways motion, the masses of the galaxies, the gravitational influence of the Large Magellanic Cloud, the Triangulum Galaxy, and the wider dynamics of the local group. A merger remains possible. A close passage remains possible. But current modelling no longer requires one unavoidable outcome. That uncertainty is fitting. Galaxies have never been simple objects with fixed destinies. They are evolving structures built from matter that is constantly moving. They grow by accretion. They change through star formation. They rearrange themselves internally. They collide. They consume smaller neighbours. They lose gas. They become quiet. Sometimes they become active again. Even a galaxy that has stopped forming stars is still orbiting, interacting, losing material, and responding to gravity and cosmic expansion. What looks permanent from a human lifetime is only a temporary arrangement on a cosmic one. A spiral arm is temporary. A stellar stream is temporary. A galaxy cluster is changing. Even the Milky Way is only one stage in a history that began long before the Sun existed and will continue long after the solar system has changed beyond recognition. So galaxies are not static islands suspended quietly in the dark. They are patterns. Enormous, beautiful gravitational patterns made from stars, gas, dust, dark matter, black holes, and the remains of countless earlier structures. And those patterns endure only because they are always changing.